Hi guys, my name is Ryden, and today I'll be presenting a review on a paper called Community Detection in Social Networks, an in-depth benchmarking study with a procedure-oriented framework. This paper was written by Meng Wang, Chaokun Wang, Jeffrey Zhu, and Jun Zhang. So to outline this presentation, I've chosen to use the 6 points for critical reading that we went through the first week of class. I chose this because the overall goal of the presentation is to get you to appreciate and understand the topic of the paper rather than focus on the algorithms and details of the formulas. So we'll start with what is the problem. So revealing the latent community structure, which is crucial to understanding the features of networks, is an important problem in network and graph analysis. During the last decade, many approaches have been proposed to solve this challenging problem in diverse ways, such as different measures or data structures. Unfortunately, experimental reports on existing techniques fell short in validity and integrity, since many comparisons were not based on a unified code base or merely discussed in theory. So why is this important? Well, intrinsic community structures are possessed by many real-world networks, such as biological data, communication networks, and social graphs, just to name a few. Given a network, it is particularly interesting as well as challenging to detect the inherent and hidden communities. Communities, which have no quantitative definition, are also called clusters. They are usually considered as groups of nodes in which intergroup connections are much denser than those intergroup ones. Just as many classic puzzles, community detection is intuitive at first sight, but actually an intricate problem. To continue on the topic, community detection aims at grouping nodes in accordance with relationships among them to form strongly linked subgraphs from the entire graph itself. Since networks are usually modeled as graphs, detecting the communities in multifarious networks is also known as graph partition problem in modern graph theory, as well as the graph clustering or dense subgraph discovery problem in graph mining area. In the last decade, lots of solutions have emerged in literature trying to solve this problem from various perspectives. So here the authors show the problem definition. They use figure 2 to show an intuitive example of results of community detection. So here you can see the network divided into three separate communities and an outlier labeled V15 just below community 3. So why is it challenging? Considering the various existing approaches, the lack of procedure-oriented framework for community detection makes it a puzzle to understand, compare, and diagnose them. Since these approaches are of various categories, a universal framework of community detection is quite difficult to be summarized and abstracted. To make a fair comparison and build a general benchmark for evaluation, it is a necessity to re-implement different approaches of various categories based on a common code base. When proposing a new approach, authors often testify their, their work via limited metrics that perform well. For benchmark evaluation, there's a need for a group of metrics which can embody full structured characteristics of communities to evaluate the approaches as comprehensively and thoroughly as possible. Let's take a look at the limitations of related work. So the authors in the paper describe that there are two related studies done which are similar to what they're trying to study. These two studies are done by Yang and others, who investigated the performances of different metrics for communities with ground truth, and Z and others made an evaluation on overlapping community detection. While these studies are similar, they fail to present a universal framework to be used for systematic, in-depth benchmarking. So it's difficult to compare and contrast when the benchmark for this topic simply doesn't exist. And so that's what this paper strives to do. So what are their contributions done from the authors? So here's a brief list of the contributions basically summarized. So they propose a novel procedure-oriented framework by formulating a generic workflow of community detection via abstracting and modularizing the key factors and steps. They review the family of community detection approaches and re-implement 10 state-of-the-art representative algorithms in a common code base using standard C++ by mapping them to a framework based on their specifics. They make in-depth evaluations on these approaches based on their benchmarks using real-world and synthetic datasets. They draw a set of interesting takeaway conclusions and provide intuitive and brief ratings on concerned algorithms. They present how to make a diagnosis for existing approaches, leading to significant performance improvements. So in this figure 1, we can see that the benchmark, it's a benchmark for community detection. It's their proposed benchmark for community detection. It separates into 4 main sections. The majority of the paper focuses on the middle section called Detection Framework, and we'll discuss what this consists of in later on in this presentation. So the benchmark for community detection has 4 core modules. There's the first one is setup, which including a set of algorithms, real-world and synthetic datasets, parameter configurations, and a unified graph model converted from the datasets. Next is the detection framework itself, a generalized detection procedure with high abstraction of the common workflow of community detection and procedure mappings. Next, after that, is diagnosis, which provide targeted diagnosis of these algorithms based on their framework, leading to directions of improvement over the existing works. And the last one is evaluation, which is a comprehensive evaluation system for the community detection from different aspects. So the detection framework itself utilizes this algorithm here, simply titled generic detect proc. So the algorithm is written in C++. However, here it's presented in pseudocode, so it's easier to understand, and you can see the procedures rather than focus on the code itself. The generic detect proc is broken up into 3 separate phases. Phase 1 is called initialization. In this phase, the graph elements need to get their initial values and form a primary community assignment. In phase 2, called transformation, the inner structures and relations underlying the network elements are transformed and clarified iteratively, resulting in a set of intermediate detection results. And in phase 3, it's called construction. In the last phase, the final result is constructed by refining the current intermediate results. So how is this benchmark used? How is it validated? So in order to validate the benchmark, make use of it, the authors employ 10 existing state-of-the-art algorithms for community detection and describe how they work under their framework. These algorithms are the ones listed below. Aggregation algorithms and division algorithms, radicai and spectral, M, KMF, LPA and HAMP, top leaders, SCP, MBDSGE, and skeleton. To the right, you'll see in parentheses that there's some text which pretty much signifies what category they're in. So in order to first determine what category they're in, the authors first reviewed existing methods of detection, of detecting of communities, that is. And from those existing methods, they derived them into different categories. From those categories, they chose 10 different algorithms to fairly represent their benchmark. So figure 3 shows some of the problem-solving perspectives of the existing methods they studied, and then the categories they broke them down into. Figure 4 shows the overall procedure mapping of 10 studied algorithms. So in order to evaluate the benchmark, the authors conducted an in-depth evaluation for the community detection algorithms within the framework using the proposed benchmark, which covers the following metrics: efficiency, accuracy, effectiveness, density sensitivity, mixture sensitivity, outliers, community distribution, and diagnosis effects. The datasets used were a mix of synthetic datasets, but also, for the most part, large scale real world networks. So the networks are listed below, um, including some well known ones such as Amazon and YouTube. So the first metric that is reviewed to evaluate the benchmark is efficiency. So in Figure 6, you can see the time costs with node scale under different phases in the framework. In Figure 7, you can see the time overheads on real world networks. And comparatively in Figure 8, you can see the comparison on the efficiency of framework implementation versus native implementation. Um, and that was one of the main ones they decided to focus on for evaluating efficiency. The next metrics are accuracy and effectiveness. So in Figure 9, you can see the accuracy and effectiveness of various algorithms on 6 metrics. And based on these results, we find that the SCP, MKMF, MSDSGE, and Skeleton perform outstandingly on networks containing many outliers. The results of these algorithms show high stability, except MBDSGE, which may be easily influenced by the scale of nodes. Moreover, it is obvious that LPA and HOMP produce eminently believable and accurate results on networks without any outliers. The next metric is density sensitivity. So in Figure 10, you can see the overall time costs of varying network densities. So what we can take away from this chart is that the increase of density of networks usually leads to higher clustering coefficients, and for most algorithms, it produces fewer detected communities. Since there are more links among nodes, so that there are fewer outliers produced by these algorithms as the density increases. In general, Radicai, LPA, and HAMP are superior to others on both the overall performance and stability. The growth in the density of a network has the strongest impact on both the efficiency and the performance of SCP. The next metric is mixture sensitivity. In Figure 12, you can see the authors compare effectiveness and accuracy. So in the Figure 12, we find that all the algorithms perform worse on datasets with higher mixture degrees, and both the effectiveness and accuracy would decrease when the communities overlap more with each other and become less discriminative. In comparison, the label propagation algorithms are more stable and show better capability of distinguishing communities from confusing mixtures. The next metric is uh, outliers. In Figure 13, we see the proportion of produced outliers. By label propagation algorithms, we hardly get outliers in a network. Compared with other algorithms studied, generally MBDSGE produces the most outliers and has the lowest coverage ratio of a network. The outliers produced by SCP, MKMF, and Skeleton are too sensitive to the value of the key parameter. The next metric is distribution of communities. So in Figure 14, you can see the distributions of community size of each algorithm. What we can take away from this is the distributions produced by CNM, LPA, and HOMP are closer to regular power law distribution. Top leaders has a different community distribution with other algorithms due to the predefined leader number. On large-scale networks, for many algorithms such as Radicai, KNMF, and SCP, as well as Skeleton, the existence of an undivided large component, which means a lower separation degree, is actually an intractable problem to be solved. So to summarize all these metrics, we can find that each approach has its own merits and faults. They vary in the efficiency of processing, have various adaptabilities to different metrics of performance, as well as different characteristics of datasets. From the perspective of efficiency, we can see that MKMF is the most efficient approach, while CNM, MB, DSGE, and Skeleton cost much more time than others. To sum it up, we have Table 9 here. Table 9 shows an intuitive summary of the approach. based on performance, adaptability, and competitiveness of the studied approaches. The general ratings from multiple critical aspects in this table, including process efficiency, accuracy, effectiveness, density, sensitivity, mixture sensitivity, as well as to what extent an algorithm can avoid producing excessive outliers. So in the below table, they use a system of ratings to compare each algorithm and how it posed with using their proposed benchmark. So what can we conclude? We conclude that this paper strives to conduct a comprehensive benchmarking study on approaches to community detection in social networks. They strive to formulate a generalized, procedure oriented framework with high abstraction and nice modularization of the fundamental factors and critical steps of this problem. They strive to re implement 10 state of the art representative algorithms by mapping them to the proposed framework and make in depth evaluations. And the authors also strive to discuss their merits and faults throughout the draw a set of interesting takeaway conclusions and provide intuitive ratings. So one thing about this paper that I was kind of expecting towards the validation was a comparison of the benchmark they proposed, the process that they proposed for the benchmark, compared to existing benchmarks or similar benchmarks. However, it's tough to make that conclusion since no benchmarks really exist. It's a rather abstract approach, abstract problem in general. Um, it's like introducing a new technology of sorts. There's no rules and regulations that necessarily apply just quite yet because there isn't anything beforehand to compare to. So I felt during the conclusions that maybe they could have stressed that a little more or still provided something less abstract because it was difficult to um, take away a more concrete or individual conclusion when comparing 10 different algorithms, even using the same benchmark. That's one thing that I felt was kind of missing from the conclusion. Well, the paper itself was fairly complicated. So these are the references used in the paper. So there was a lot of work put in this paper from the authors, a lot of material. It was difficult to even shorten this presentation to a reasonable amount of time. On that note, if you have any questions or something that you'd like to discuss more, you can always email me at rsummer3 at fau.edu. And I'll answer what I can based on what I learned from reading the paper. So thank you for your time, and have a good rest of the day.